So this unit is Newtonian mechanics, and the kind of bread and butter of this section is F equals ma. The net force is going to be proportional to and equal to your mass times your acceleration. And so what I'm going to do is just kind of run you through some pretty typical type problems, and this should help you with your second test. So here I've got a box on a flat surface. There's some friction going on here. I've got my weight vector, I've got my normal force from the surface, and then I'm pulling the block, but I'm pulling it at an angle theta. Now, because I'm pulling at an angle theta, well, that's kind of altering some forces. So my normal force is now decreased because I'm pulling up at an angle. Here's why. If I sum my forces in the y direction, now that's equal to the mass times the acceleration in the y direction, but generally we can assume that I'm not pulling up so hard that I'm actually lifting the block off the surface. So my acceleration in the y direction is going to be 0. Well, I have some forces that are in the y direction, so let's do what this equation tells me. It tells me to sum those forces. Well, there's Fn, there's Fg, but now there's also this y component here, Fty. That is going to be equal to 0. Well, I don't know what Fn is. Let's say I'm solving for Fn. But I do know that Fg is mg down. So that's going to be minus mg and then plus Fty. Well, Fty is the opposite to this angle. So it is directed up, so it's going to be plus Ft sine of theta, because again it's the opposite. Now to solve for Fn, well, I would add mg to the other side, and then I would subtract Ft sine theta. So you see that if I wasn't pulling on the block, in other words, if it were just sitting here, well, there'd be no Ft, which means it would just be Fn equal to mg. But because I start to pull up, I am decreasing that normal force by exactly how much I am pulling up. Now, because of that decrease in normal force, there's also a decrease in the amount of friction, because friction is given to you as mu k times Fn. Well, if Fn is lower and mu k won't change because that depends on the two surfaces that you have, well then your frictional force will be lower. But if I'm pulling this at a constant speed, that tells me a couple things. One, my acceleration is 0, which means that my net force in the x direction is also 0, which means Ftx is going to be equal to how much friction I have. So that's just an example of a block being pulled at a speed, at a constant speed with a couple forces acting on it. Now, another classic style problem is one where you've got an inclined plane and you've got a block on it, either at rest or sliding down. If it's at rest, there is still always that block's weight vector, and its weight vector is always going to be straight down, Fg. But if it's at rest, you got to think about, okay, well, I've got normal force coming up like that, off perpendicular to the surface, and if it's at rest, well, then I've got some force keeping it there, which means I've got static friction pulling it back up the ramp. Because if I make normal force my y-axis and the ramp itself my x-axis, you can clearly see that I've got some weight component pulling it down the ramp, okay, an Fgx. And in this case, if this is theta, then the angle from the vertical out to the weight vector is also theta. Well, then Fgx is going to be Fg sine of theta, because this is the opposite. Well, if it's at rest, that means that Fs is Fgx, which is Fg sine theta. And so just think about this. If I increase the incline of that ramp, if I increase theta, well, the closer theta gets to 90, the larger sine of theta becomes. which means if I increase that angle, the more and more static friction I would need. Static friction reaches a point where it can't exceed and it breaks and starts to slide. And this area would be kinetic friction. So kinetic friction would then just be equal to mu k times Fn. Now, if you do this equation, Fs is mu s times Fn, that tells you the maximum static friction that you can have. Because static friction can change depending on how much force is present. So this is from your lab where you barely pulled, and then it started to slide. Static friction increases, and then it breaks, and that block slips, and it slides. So hopefully this gets you a pretty good start on your inclined plane type problems. I'm going to do one more problem where we've got an object in equilibrium. So let's say I've got something like this. Let's say I've got a block being suspended from two strings. And this string is at an angle of 60, and this string is at an angle of 45. Okay, well, I've got two tension forces going on here. I'll call this one T1, and I'll call this one T2. Now, I still have this block's weight vector, Fg, which is mg, and this block is in equilibrium. Anytime you're dealing with a problem with forces and your forces are going in two dimensions, you are typically going to have to deal with both of those dimensions, meaning you're going to have to sum your forces in the x direction and you're going to have to sum your forces in the y direction. Now, since the block is in equilibrium, both of those are going to be equal to 0. And if you look, you have two unknowns and you have two equations.